Hello, statics class. This is our fifth equilibrium analysis example. It is still February the 12th, and this recorded lecture is serving in lieu of our snowed out meeting time at Skagit Valley Community College, or just for your general studying pleasure. This is a pulley problem. And so again, we have not introduced friction yet. So if you've already studied your capstan equation, you can forget about it. We'll assume that there is no friction and that therefore the tension in a rope or a cable is going to be the same from its initial connection point all the way through, unless it's connected with like a fixed pin, in which case it's not continuous. So plenty of time for tension transfer with our frictional pulleys later. For now, this is just frictionless, which is a very good assumption in a lot of cases, like if we have really smooth bearings or something that are going to turn the pulley and we're not sliding a rope across it. So there's a lot of real life situations that are frictionless to a good enough approximation. So this is not just esoteric knowledge here. So here's our setup, and apologies for the somewhat crude drawing. This was no doubt made on the ADX interconnect coming down to CUL earlier in the semester. So we have sort of a ceiling with some pins. So we have pulley number 1, which is attached with its own kind of bracket support. And then pulley number 2 is being held up with a rope that goes over pulley number 1 and then is fixed connection to pulley number 3. So the rope only has the travel path from the center point of pulley 2 up over pulley 1, and then it's tied off at the center point of pulley 3. Then we have like a big cable or a chain. It's drawn in a heavier line here. So it's attached to the ceiling and it goes under pulley 3, over pulley 2, and then it's attached to a weight B. In addition to all that, we have a weight of 120 newtons hanging off the center line of pulley 3. So we have two continuous cables, so to speak. So we have a cable that goes from the center line of pulley 2 up over pulley 1 to the center line of pulley 3, and then we have this long heavy rope or heavy chain that comes under pulley 3 over pulley 2 and then is attached to weight B. And the question is, what would weight B have to be to keep the whole system in static equilibrium? It's like, okay, great. Let's just draw some Fbds until we get what we want. So given that there's only one way to find the weight explicitly of B, and that's to draw an Fbd of the weight on B, we're going to start with that. So I've got weight B, and it has a force in the downward direction of its weight, which is being opposed only by the tension in that heavy shaded cable, which I'm going to call T2. So great. I know that the weight is going to have to be equal to T2. Now all I have to do is find out what T2 is. Okay, now I'm going to start drawing Fbds of the pulleys and see if I can't get that isolated. So I'm just going to start at the top with pulley number 1. So it's got a force upwards from the bracket attaching it to the ceiling, which is being opposed by the downward force of T1 in two places. So F1 equals 2 times T1. Well, that's nice, and that keeps pulley number 1 in static equilibrium, but didn't do much to help me find the tension in pulley number 2. Excuse me, tension in T2, which is what I want to oppose the weight. So now I'll draw an Fbd of pulley number 2. Notice I'm not going in any logical order here. I probably could have optimized this by starting with something else, but you know, I'm just marching through it, and I'm going to rely on my equations of equilibrium and my Fbds to eventually get me there, which it will. So I look at pulley 2. Pulley 2 is being held up with T1 because it's attached up to pulley number 1, and it has a downward force equal to T2. So okay, now I have a relationship between T1 and T2. Okay, that's good. Be nice if I knew what T1 was, because then I would know T2 and then I would know weight B. Okay, let's hope that we can get that out of free body diagram number 3, which of course we will. So we go over to pulley number 3 and we notice it's being pulled up on by T1 It's being pulled down on by the 120 Newton force that was applied directly to the pulley, and it's also being pulled up on by T2 twice. Now we didn't lose any friction anywhere, so T1 is T1 is T1, T2 is T2 is T2, so now we have the relationship we need. We have two equations, this one and this one, and two unknowns, T1 and T2. We solve two equations and two unknowns. We get a T2 of 30 newtons, which is equal to the weight. So really the only equation I didn't need was this one over here for pulley number 1. This really didn't do anything for me. That was a bit of a waste of time. I needed the FBD on pulley 2, the FBD on pulley 3, and the FBD on the weight to get what I needed from this. So this is very, very classic way you do pulleys and cables. This was a frictionless one. Had we had to incorporate some kind of frictional component, we would have ended up with T's that changed as we went around the pulleys. And so we would start grabbing our handy capstan equation to write relationships between those based on the angle of contact and the coefficient of friction, and would have simply put it together that way like a friction problem. But since we could discount that, all we had to do is add up tensions. So that's it for that problem. Lots of FBDs and equations of equilibrium to get what we want. No mysteries.